So now we are moving to our main session, and I'm very excited to introduce Rafael Poyatos from CREAF, who's going to talk about SubTlux initiatives, and particularly the role of transpiration of trees and forests using SubTlux database, which they've constructed at CREAF in Spain to look at species level water use strategies for the quantification of ecosystem transpiration. And over to you, Rafa. You're on mute still. I don't know if you can unmute yourself. Perhaps not. No.
Now you should.
Now you should. Okay. Rafa, are you there?
Yeah. Can you hear me now?
We can hear you. Yeah. Can you share your screen?
Okay. Yes. Right. Okay. Can you see my screen now?
Yeah, we can see your whole point.
Yeah. A minute. Okay. Now?
That's perfect.
Okay.
Yep.
Sorry. Yeah. So good morning, everyone. It's 6 in the afternoon here, but yeah, morning to all of you. So yeah, I'm Rafael Poyatos from CREAF, and I'm going to really thanks to the organizers for inviting me to talk about SubtropicsNet here today, especially given that the invitation comes from Ameriflux and all what it means to me, because yeah, all these regional networks were inspiration for me to start this initiative. So yeah, I'm going to show today introduce you to the SubtropicsNet database and show you some examples of its use, to understand how species regulate transpiration, and also towards the quantification of ecosystem transpiration. And it's something also Jake will talk later in the next talk. Okay, so yeah, I will start briefly introducing the topic. I guess most of you will be familiar with all this information, but just to remind you that yeah, transpiration, the flux of water evaporated from within and the plants, it's 60 to 70% of terrestrial evapotranspiration, represents 40% of land precipitation. And I always like to remind people that that it's the same amount of the global runoff.
Rafa, could
yes.
you speak up a little bit? Some people, I find your audio perfectly clear, but some people are having trouble with volume.
Okay. Okay. So yeah, to speak louder. So yeah, as I was saying, yeah, transpiration is a really important component of global water cycle, but it's also not only about the amount of water that is used by vegetation, also the way this water is used by vegetation, how this water is used. And this is just an example of a drought impacting Australia, and this patch of surviving calitris, a very drought resistant species, surrounded by all these eucalypts affected by dieback. So in the end, how plants control transpiration, it's important to understand vegetation functioning and dynamics. So all of you will be familiar as well with the several methods that can be used to estimate the evaporative fluxes from land. And if we're working at smaller scales at the leaf, at the plant level, we know it's relatively easy to measure transpiration individual leaves, and going from there to whole plants, even if logistically it gets difficult if we try to measure transpiration in whole tree chambers. But on the other hand, if we have all these methods that work at larger spatial scales, starting from eddy covariance and ecosystem scale, catchment water balance or remote sensing methods. They also provide like more operative measurements, not that they can provide more long-term records, but it's also more difficult to get the signal of transpiration there. So I really isolate the signal that comes from transpiration and separate it from the rest of the evaporative sources. So yeah, even if transpiration is a really relevant process, we find it still like difficult to measure. But so starting in the late 80s and in the 90s, subflow methods started to be widely used in ecophysiology and forestry and related disciplines. And with these techniques, we basically measure the flow of water. Most of the time, we applied subflow sensors in the main trunk of the trees. And this provides an integrated measure of the water flow at the whole plant level. No? So we get this macroscopic view that integrates all the fine detail variation in anatomy, physiology, and structure in different organs of the tree. Okay. So how these methods work, they basically use heat as a tracer of the movement of sap within the tree stem. Some of them use the dissipation of heat that is continuously generated by a linear heater inserted into the tree's sapwood. So these are the thermal dissipation method is the most widely used, and it's based in these principles. There are other methods like the heat field deformation that also take advantage of this dissipation in 2 dimensions. There are also another group of methods that they don't track continuously generated heat, but short pulses of heat that are tracked in the sapwood, and these are the heat pulse methods, and there are several configurations of these, and I won't go to much detail here. And there is also a third family of methods, which is heat balance, that apply heat balance equations to entire sections of the trunk or to parts of it, to sections of the same trunk. So basically, these sensors are constructed, or these probes are constructed from temperature sensors embedded in needles and also resistances, which work as the heaters that also inserted in the sapwood. And from the outside, it just looks like needles inserted in trees and typically covered by some reflective material, because we don't want the influence of like external natural gradients on our measurement. Okay. So all these studies, all these subflow data, like remain sparse in the and dispersed in the literature, but it was not centralized anywhere. And yeah, inspired by, in part, that all what the regional networks and the global networks of ecosystem flux measurements did in the past, I thought it would be a good idea to collect all this data. So this is why we started the SubtropicsNet initiative, like in 2016, and we started to ask all people having worked in subflow to send the data to start building this database. So we work with, or we collected data that is at the plant level and also at sub-daily scale. So it's subflow per plant or per unit sapwood area, together with in situ measurements of meteorology and soil moisture, and also some metadata that relates to stand variables, the leaf area index, basal area, other plant attributes like tree size or tree DBH or tree height, and also other technical details related to some of the measurements, both the subflow and the environmental measurements. Now, this database is already available. So the initial idea was that this database should be available for everyone to work on, and it was published in Zenodo last year, and I think it's already close to 2,000 downloads. So I'm really happy that people are using this database. It's not only the data that we provide, but there is also an R package called SubtropicsNet, and that has some functionalities to query the data, because this database you have to download into the database, but we provide tools in the package to to work with a subset of the data. You can query by species or by biome or any other metadata. We provide also functions for the temporal aggregations and also for data visualization. Okay. This database, SubtropicsNet database, now has more than 200 data sets globally distributed. Although it's true that most of the data sets are concentrated in Europe and also the Eastern US, in general in Eastern North America, and but we have some data sets also in Australia, South America, and Asia and Africa. But if we look at the bioclimatic coverage, it's also true that we have all the or most of the terrestrial biomes represented. But again, most of the data set are concentrated in what we see here at woodland, shrubland, which are mostly Mediterranean sites, but also in temperate forests. Okay, but this database, of course, is unprecedented in its volume. It has data for more than 2,700 trees and representing 175 species. So yeah, we can also see the distribution by vegetation type. Now that we have mostly data from evergreen needle-leaf forests, deciduous broadleaf, and then evergreen broadleaf forests. Okay. So after this brief introduction of the database, I wanted to show you a couple of examples of what we've been doing recently with this database. And the first question I would like to address is what is the role of plant traits and climate in determining how plants regulate transpiration across species. So this is a first study focused on species water use strategies. Okay. So first of all, I will present the broad framework here, and we'll go later into some details that we need to understand how this was done. But first, we had to summarize the environmental responses of transpiration using our SubtropicsNet database. So we summarize these responses in 3 parameters. So one is this 3 canopy conductance per unit subwood area, the reference conductance that I will explain later what this is. It's kind of a proxy of an optimal conductance. And then we have 2 sensitivities, one beta sensitivity to BPD and a beta sensitivity to soil water content. So our idea was to embed the responses to environmental variation in these parameters. So this is what we call water use parameters. And we wanted to relate these to some plant traits that are measured at the species level and that are more and more available in trait databases, okay, and that are important mechanistic traits for plant drought responses. So one first trait is the psi TLP. So this is the turgor loss point. Here expressed in absolute values or larger values means like more drought tolerance at the leaf level. Okay, this leaves able to withstand more negative water potentials. Then we have psi 50 or P50, this water potential at which the xylem, in the stem xylem in this case, loses 50% of the conductivity. So here again it's an absolute value. So larger value means here species which are more resistant to embolism. And then we have the conductivity of the xylem, stem conductivity, so the capacity to transport water. Okay. Another set of traits more related to structure are these the rooting depth, okay, the rooting depth of the species level, the leaf size, the individual size of the leaves, and also the Hoover value, which is this ratio between subwood area and the leaf area, providing a kind of a balance between the conducting to transpiring area. Okay. So our question here was whether these traits were able to explain these water use parameters, meaning that these traits are able to represent the environmental responses of different species in regulating transpiration, and how this was modulated by climate, so mean annual temperature, mean annual precipitation, and tree height. So just an example of how we, first of all, of course, we need these water use parameters. So we first calculated the this canopy conductance at the tree level. And this was expressed per unit subboot area. So we know that physiologically it makes more sense to express this per unit leaf area, but the matter is that we lack leaf area data for many of these species in SubtropicsNet. So that's why we work the subboot area level. So we have here two examples of the models we fitted. So we fitted these models of these canopy conductance as a function of log transform BPD and soil water content, no, in additive responses. And what this means is that then from these models we get these parameters, which is gref, no, the conductance at a reference level of BPD, which is 1 kilopascal, and also at a level of soil water content that is not limiting, so that we picked it was 0.5. Okay. So this gives you this idea of an optimal conductance. From these models, we extracted this slope of related to BPD, this beta BPD, giving us the strength of decline of conductance with BPD. So in this case, we change signs, and of course, conductance declines with BPD, but we change the sign of the slope here. So meaning higher values of beta BPD means like more sensitive species. Okay. And then we quantify the beta soil water content, as this deviation of the curves as the soil dries. So in the first example, Quercus vaginia in the top, we show a species that is not sensitive to soil water content. Okay, all the curves relating conductance and BPD kind of collapse into a single curve or are very close together. While for Quercus robur, which is a species which is more drought sensitive, we have this variation from wet soils to dry soils in this lowering the response to BPD. Okay. We obtained these parameters for 142 species, and we started looking at the bivariate relationships. And this is an example of two relationships, but in the table below, I summarize these relationships. And we show that species with higher reference conductances had also higher stem conductivities, deeper roots, and larger leaves. Okay, and also they show were negatively related with these absolute values of P50, and also with the Huber values. Meaning that these species with larger conductances were also related to higher vulnerability to embolism. Okay, and also showing more investment in leaves rather than in subboot, for example. And these results, we also observed the same results for BPD, with the difference that we didn't observe any relationship with turgor loss point. And we were kind of surprised that turgor loss point didn't emerge as an important variable here, because in other side level studies, we know that turgor loss point was related, for instance, with the sensitivity to soil water content. And also talking about the sensitivity to soil water content, we also showed that these species that were more resistant to embolism, higher absolute values of Psi 50, were also more sensitive to soil water content. That was also kind of surprising to us. Okay. So to simplify a bit the analysis, and because some of these traits are related to one another, we conducted a principal component analysis, and we summarized this trait information. So in the first component of this analysis, it was positively related to deeper roots, more conductive stems, and larger leaves, and negatively related to this resistant to embolism and to this more production of subboot related to leaves. So this we interpreted this axis as an axis of like more efficient water use, okay, like a more acquisitive strategy in terms of water use. And the other dimension was related, explained much less variability, and was related negatively with the turgor loss point. So higher values in this axis meant also less tolerant leaves.
Rafa, just a 2-minute warning.
Okay, so in the end, what we got is the full analysis with climate and water use parameters and the traits looking at these water use parameters are related to one another. Higher conductances in these solid lines mean positive relationships. So higher conductances related to higher sensitivities to BPD and soil water content. The trades, we show also these positive relationships in the black lines, no? Like more efficient trades are also related to higher conductance and also higher sensitivities to BPD, for instance. But also the role of climate, no? That was not directly related to the water use parameters, but through the traits and also importantly through the size, so the tree height. No? So higher precipitation, no, involves like more productive vegetation or like taller trees and species with more efficient traits that have an impact also on the regulation of water use. Okay. And the last thing I want to talk about is how can we scale this SubtropicsNet plant level data to ecosystem level that makes more sense to work if we want to match, no, for instance, with ecovariance data. So we have first provided a scaling based on the species mean subflow per unit basal area, okay, because we have the basal area of the plots, and we can have a first order scaling of these fluxes, and these are just an example from 16 sites. But also we wanted to explore the data-driven and also size-dependent scaling. So this is based on random forest models of subflow, including BPD, DBH, and also variables accounting for the seasonality and also the species. And this was a test in a Mediterranean forest here near in Barcelona. Okay. So providing this framework for scaling allows us to integrate or include these size effects on transpiration, and also allows us to use maybe data from forest inventory or from ecosystem LiDAR that can be used for the scaling of transpiration. And as you can see here, we provide larger transpiration estimates compared to the blue line, which is the species level scaling, which doesn't take into account this size dependency of subflow. Okay. So just to finish, wrap up saying that the plant traits together with climate and tree size can explain this environmental regulation and transpiration across species. And this can be useful because there are more and more trait maps that can be used to extrapolate water use strategies and be used in models. And also on the scaling size, we showed that this size-dependent scaling can provide an alternative to a basic species mean scaling. So we take better into account the size dependencies, and they can also take advantage of data on forest inventory or LiDAR that can be available in the future. So yeah, thanks, and sorry for the technical problems at the beginning, but thanks to the co-authors and also especially to the contributors to SubtropicsNet and the users. Thanks.